20K from my account to another account. So I've sent a request saying transfer 20K from account A to account B. Okay. And in the case where the message got lost, the request got lost, it means the message never arrived, and so the transaction was never done. So if I send the request again and it arrives, then the transaction will be done. And maybe I will get back a result saying the transfer has been done. But what about in the case where the message arrived and it is the reply that got lost? So I sent the request, transfer 20K from account A to account B. The reply got lost. So in the application, you do the send again. And you send another request saying transfer 20K from account A to account B. And hopefully there is money in that account. So that means a second transfer will be done. Because remember that the connectionless protocol does not number messages. Messages do not have numbers 1, 2, 3. Every message is independent. So the second transfer message will just be taken as just another message. So the application will just think, okay, you want to transfer another 20K, fine, let's transfer it. So it will transfer another 20K to account B. And maybe even the response for that one gets lost also, and the application loops back and sends a third request. That will be the third transfer. So the protocol is not able to realize that this is a duplicate, or this is the same request that had been made, only that it has been repeated. Why is it not able to tell that? Because the protocol does not number messages. Every message is taken as an independent message or request, and it is acted on as an independent request. Even if they are similar, they are not related. So that is just to show you some of the problems of trying to program with a connectionless protocol. So in the example I've given, 60K will be transferred from account A to account B, when in fact, all that the program wanted to achieve was to transfer 20K. So that's an anomaly. However, if you are doing the balance type of request, where it just says, show me my balance. So you send the request gets lost, or the reply gets lost, and the application sends a request for balance again the second time. The request will be executed and a reply sent. And even if it gets lost, you can send another third balance request to the server, and the server will execute it without any harm, because the balance is not being changed. It's just reading the balance and sending you what the balance of the account is. So that shows that there are some operations that can be performed repeatedly without any harm. But there are those operations that can be performed repeatedly with a lot of harm. And if you look at that last bullet, it says when an operation can be repeated multiple times without harm, it is said to be idempotent. So in the example I've given, it's the balance that is idempotent, because it can be repeated multiple times and it will not affect anything. Just reading the balance and sending you the balance, you can do it 100 times. However, the transfer or credit or debit, those type of operations that actually change the value of the balance in your account cannot be repeated several times without harm, because every request will be executed and it will make a change on your account balance. And the next time it is sent, the server doesn't know it's a repetition. It just thinks it's another operation to be done. It does it, it changes your balance every time it is sent. So that type of operation is non-idempotent. That means this, that when you are programming using a connectionless, when you are programming any application, you need to think through whether or not those operations or requests you're making to the server are idempotent or non-idempotent. If you have many operations that are non-idempotent, then it's not worth using the connectionless protocol. Because yes, you may recover from the failure and you may retransmit the message, but the effect of the retransmission on your application will not be good. And this can happen for any application. So you need to analyze the application that you're programming and think about it and think whether or not the operations are idempotent or not. So in summary, making the protocol, the connectionless protocol, resistance to occasional transmission of failures is not a trivial matter. Programming well with connectionless protocol is not a trivial matter. You have to think through the logic of your program to see whether if you recover from failure or you try to overcome the failure, the effects it will have on your application in general. Now, the connection-oriented protocol, of course, is more reliable, and the repetition is done at the transport layer, not at the application layer. The repetition that needs to be done to overcome the failure is done by the transport layer. So that means that a connection-oriented protocol can work quite well within a wide area network, where you expect there to be more failures because there are many more intermediate nodes in between, and any one of those intermediate nodes can fail. And so it would then make your message which you have sent maybe not reach its destination. So the rate of failure is higher, or the probability of failure is higher. So in such situations where you know that the likelihood of failure is much higher, then it is better to use the connection-oriented protocol, especially if you have many non-idempotent operations. Now, remember that even if there is failure, but the type of operations you have are idempotent operations, then you can still use the connectionless, even over a wide area network. If all I needed to do was the bank balance request, and I know the wide area network like the internet is unreliable, I could still do it. Only maybe I may need to repeat that request many times to get a response. But I can do it without any harm. It will be harmless. So I send the first request, it gets the reply gets lost. I can send again, give me the balance, a second time, a third time, a fourth time, even 100 times, and I'll still get back the same balance. So the only problem you will have over a wide area network, if when it is highly unreliable, the only problem you'll have that you may have to repeat the request many times if it is idempotent. But if it is non-idempotent and the network is unreliable, it is better to use the connection-oriented. So here it mentions that virtually all internet application protocols are based on a reliable TCP/IP connection. I hope you know the application protocols on the internet, the HTTP, the FTP, those application layer protocols that are in the internet reference model. Most of them are programmed using the connection-oriented. For that reason that we have said that the network is typically unreliable. I think we mentioned this many times when we were talking about the IP layer. The IP layer is built to be unreliable. It makes no effort to retransmit. But the TCP IP, the TCP is the one that tries to recover from the failures of the network. So I think really what I'm trying to say is that application programming requires for you to think about what is the application trying to achieve? Are there operations that are idempotent? Are there those that are non-idempotent? And therefore, based on that, which is the best protocol to use for that application? Now, of course, you are aware that a connection-oriented protocol has three phases. You set up the connection, you send the request, then you terminate the connection. Now, the only disadvantage or the major disadvantage with connection-oriented protocol when you use it within the application is the time it takes to set up a connection and to tear it down. Because remember, there's a three-way handshake in setting up the connection. There's a four-way handshake in closing the connection. And those have nothing to do with the data transfer. So suppose I want to do a balance request. I want to use the banking service and I want to request for my balance. And that's all I want to do. Is it worth it setting up a connection, which will take time, then sending the request for balance and getting a result, and then tearing up the connection? Is it worth it? If you think about it, will the time for setting up the connection plus the time for tearing it down, the sum of those two be greater than the time it takes to get a result from the server? And will that be worth it? So if it takes a lot more time to set up a connection, only to send a very small request to get a reply, you have to think about it whether it's worth it. Is it worth it? In the case of the balance request, I don't think it's worth it. But in the case of maybe transfer, it may be worth it. Maybe it is expensive, but at the end of the day, you will not mess up your bank account by doing a transfer 2-3 times. So you may say for that reason, it may be worth incurring the cost of setting up and tearing a connection in order to attain reliability. So you also have to weigh, is it worth setting up and tearing a connection to do a certain operation? So in a nutshell, I'm just trying to say that the choice of protocol that you use in your application needs to be thought through based on the type of application, the type of operations that your program is actually carrying out, the effect of those operations on your application, vis-a-vis the cost of setting up and tearing a connection. You need to evaluate all that to come up with the best decision of which one is best for your application. Now, we had started up with the layered architectures. I think that's where we started in the morning. And we talked about layering being done within the data communication domain, and all the protocols are layered one on top of the other, and each layer uses the services of the layer below. And I think you know that whole process. But then I said that layering can also be done for the application, and so we said that you can split the interface and the processing and the data level. You can split them into 3 different layers, and then they can interact with each other, where the interface will request for service from the processing layer, and the processing layer will request for service from the data layer. So it depends. In your application, you can have more than 2 layers. You can have more than the client and the server. You can have a multi-tiered application where you have 3 layers. And in 3 layers, you'll have separated the interface from the processing from the data. That will be a three-tier application. Client server would be 2-tier application. And of course, you may have other applications that may require more than 3 tiers. Okay. So the question then is, how do you split the 3 tiers? Of course, the impression I may probably have given you so far is that each layer sits in its own, on its own computer, or is separate from the others. They are totally distinct. But if you look at this diagram here, the first diagram A, you notice that in this particular scenario, the interface is actually split so that part of the interface sits in the client machine and the other part of the interface sits in the server machine. So it's even possible to split a layer so that it spans more than one tier, that is. So there are various ways to split your application when you're doing the client-server architecture. Each of these is a possibility. And if you check in your textbook, you'll find out in what context each of these ways of splitting your application is applicable. So I want to leave that to you as an exercise so that you find out which scenario would require you to split your application in a particular way. Those scenarios are described in your textbook, so I would like you to look at them. But all I want to say is that those three layers, you can split them depending on how your application, on the circumstances of your application. Yeah. So please make sure that you look at that part of your textbook and you read about that. As I think from the textbook that I've looked at, I think it is section 2.3.2. As I've said, there it talks about the multi-tiered architecture. It describes this diagram here and what each of those scenarios represent, what type of application would require for you to split your data in that way. I hope you see the difference that, for example, in the first one, only the interface is split into two, and the application part or the processing part and the data are all in one machine, the server machine. In the second one, you notice that the complete interface is on the client machine. In other words, the client only has the interface of the application, and the server has both the processing and the database. In the third one, you have the client interface, or the interface that interacts with the users, plus a bit of processing. So the application is split into two, so that there's a bit of processing on the client side, and then the rest of the processing is done on the server side. In the fourth one, you have the whole processing being done on the application side, and so on and so forth. So depending on which application, you need to think clearly which one will give you the best outcome for your application. So as you look at those alternatives, I hope you will understand why they're split in that way. Any questions? As I've told you, please make sure you read that section. I gave you this reading assignment at the beginning of the semester. I wonder whether you have read it at all. But now, perhaps is your last opportunity to read it. Any questions? Are you following what I'm saying or not? You're just quiet, so I'm not sure
Yes.
what it means.
We're following. We're following. We're following.
All right, so I'll take it that you will look at that. And notice that there are examples also in your textbook about systems that we commonly use that are built on this type of architecture. There's the network file system, and there is the web. They are both built on the client-server model with the 2 tiers. So it would be interesting for you to find out in this network file system, what part of the application or what part of the application or the system is on the server side and which part is on the client machine. And I think I emphasized this before. In my opinion, the machine is referred to as client or server depending on which software sits there. So it is the server software that sits on a given machine, then it's called a server. If it is the client part of the application that sits on that machine, it is called the client machine. It is not the other way around, that it is the client machine that determines what runs on top of it. It is the application that determines what the machine will be referred to. But also don't forget that a server can also be a client in different contexts. Which diagram am I looking at? Okay, let me just use this diagram to explain what I mean. If you look at the second diagram, the user interface sits on the client machine. And it assume the user makes some choice based on the interface they are presented with, they choose what they want, and the request is formulated and sent to the application layer, to that middle layer. Now, if the middle layer requires something from the database, it will have to also formulate a request and send it to the database. Now, at that point, the application of the middle layer is a client. When it comes to the application talking to the database, the application is a client. So it sends a request to the database and the database sends back some data. Now, when it comes to the user interface talking to the application, then the application is the server. And the user interface is the client because it's the one that sends the request and waits for a reply. So a server may play multiple. It may play as a server and as a client at the same time, depending on the context. So you also need to take note of that. In certain cases, it will be a client, and in certain cases, it will act as a server. Given the definition that we are given, that it is the client that sends the request and receives a reply. So any program that behaves that way is a client. It sends a request and gets a reply. The one that receives the request and sends a reply is the server. So in whichever context, you can easily find out which is the client and which is the server based on their behavior, the way we have talked about it. Right. Okay, so the question of the types of servers, I believe by now you know the types of servers that you can have, but let me just mention them again. We can have different types of servers. Of course, we have talked about connectionless and connection-oriented servers. It depends on which protocol they're using. If a server is, you can access the service on a server based on connectionless protocol, then it's a connectionless server. If you talk to the server using a connection-oriented protocol like TCP, then it's a connection-oriented server. So the connectionless and connection-oriented makes sense. But then there's the issue of iterative versus concurrent. Now, in simple terms, the iterative server is the one that serves users one at a time. Note, I said user. One user at a time. If it's connection oriented, or one request at a time. If it is not connection oriented, like it's a connectionless protocol, it will serve the requests one at a time. If it is connection oriented, the way we have talked, where you have to first create a connection and then use the connection or transfer data and then close the connection, then iterative basically means you serve one user at a time or one connection at a time. So you loop, you need to loop through your program to, once you finish serving one user or one request, you go back and pick the next request, serve that one to completion, and so on and so forth. And concurrent is where you now serve multiple requests or multiple connections at a go. Now, of course, there's the issue of stateful and stateless. You can also distinguish servers by whether they are stateful or stateless. I'm not sure how you interpret this stateful and stateless, but I'll be glad to hear what you understand by stateful server and a stateless server. Anyone who knows what a stateful server is or a stateless server is? Okay, let's have someone. Roman? Mm-hmm. Mm-hmm. Every request must be complete. Every request needs to be complete. Now, do you think, okay, I've understood you, Roman, and I agree with you in many ways, but I think there are just some distinctions you need to make. But I think from what I've understood, you're trying to say that a stateless server, there is no information kept about the operation that was done. Once an operation is complete, all information about it is deleted. And so if you were to repeat that operation again, you would have to give the complete information about it. Yeah. If it is stateful, once you have done the operation, there's some information you retain so that if you were to repeat the operation, you don't have to provide all the details. I remember in the morning class just referring to your answer, Roman, when you were saying that you you request for to order a book, and you send the details of the book, which is the title and the ISBN. And then I noticed that you sent that the server sent you back again the title and the ISBN. And I was asking, why was it necessary to send you back the title and the ISBN and you already know it? It's the client that actually gave the information to the server and said, please order for me this book. I mean, if it were me, I would have probably just sent the order number, because the one who ordered the book already has the details. But it's something like that, although maybe not quite. It's something like that where there's some information that is kept so that there is no need to repeat that information again next time, something like that. Okay, but let me ask you, assume you are interacting with the file service. And from what we said, a file service requires that you open a file, then you read and write a file, and then you close a file. Do you think that's a stateful service or a stateless service, the way the operations work? Mm, mm, mm. Okay, I get you, but let me just prod you a little bit, because I understand what you're saying, but I think there are certain things that you're not mentioning. So when I open a file, do you remember the arguments that I provide for when I'm opening a file? But you have written an application where I insisted that you use files. So I believe you opened files, you read and wrote through the files as you were entering the details of the books and the details of the orders. I want to believe you have another file for orders. So you have used it. So what are companies and open operation? Mm-hmm. Mm-hmm. Okay. So you have the name of the file and the mode in which you want to open it. Okay. Now, when you read the file, what do you send? What are the arguments of the reader file? What do you call that pointer? Yes, it's a file descriptor. And remember, we said that a file descriptor is simply just a number. Remember the file descriptor table when we were talking about sockets? It's basically just a number you are returned, and you can even check whether the number returned indicates whether or not a file was opened. Yeah. So the subsequent operations that you perform on that file, you use the descriptor, you don't use the name. So that already indicates to you that it is stateful. Remember that stateless means each operation is complete on its own. So that if that read operation were to be complete, then you would say read, and you would give the file name, and you would give where to start reading from up to where to stop reading. You would give all those details. If it was a complete operation, let me open this and just move to a different frame. Assume you want to read a file. Assume you want to read a file and it has several lines that you can read. The normal read operation has a file pointer, and the file pointer is not the file descriptor, remember. File pointer is the one that stops where you last read. So assume each of these lines is 80 bytes. Let's just assume each of these lines is 80 bytes. Now, if I do an open of the file, assume I do an open. Let me just get a text box here.
Are you present?
Oh, I have not projected.
Yeah, you can't see.
Sorry. Okay, so believe now you can see it. So I'm saying this is my file which I want to read. Now, if that's a file I want to read, the normal operations would be open, and then I would have the file name, whatever that name is. Of course, I would give it in the form of the directory where it is, file name, and then the mode. Okay, I would open it. And then I would do read, and I would use the file descriptor. And I would say, for example, read 100 or 80 bytes. Okay. I would say something like that, and I would give the file descriptor. Remember, the file descriptor is what was the file descriptor is what was returned when you open this file. So assume I opened this file and I got back a file descriptor. So file descriptor is what you get back when you open the file. It's like the socket descriptor. So with a file, you also get a file descriptor. So subsequent operations on the file, you don't use the file name, you use the file descriptor, for example. So if I do another read, which bytes will I read? So I'll do another read with the file descriptor and I say read 80 bytes, let's assume. So which 80 bytes will I read? The first 80 bytes or the second 80 bytes or what? Each line is 80 bytes, let's assume. So the second read will read the second line. Yeah? Yeah. Under the normal file operations, that's what it will do. Because when you read the first 80 bytes, remember when you open the file pointer is at the beginning. When you open the file, just by opening the file pointer is there. So when you issue a read statement, you say read the first 80 bytes, it will read the first 80 bytes and it will stop at the end of those 80 bytes. It will position the pointer there. When you say read another 80, it will again now start reading the next 80 bytes. And then the file pointer will be located or fixed at the end of those 80 bytes. So that you never have to say read from byte 90, from byte 81 to byte 160. Because that's really what it is. This one here, this second read here, is basically saying that you are reading from this second read here is actually reading from byte 80 to byte, 81, sorry. It's actually reading from byte 81 to 160, Yeah, if I do another read, and I read file descriptor 80, I will be reading from byte 161 to whatever that is 224. Is it 240 or what? 60 plus 80 is what? 240.
Yeah, 40.
Something like that. But you see, the reason why you are just able to say read for me the next 80 bytes is because there is this thing, file pointer. That information is kept by the server or by the file system so that it knows up to where you last read. So you never have to tell it where you stopped in the last read statement. It should know because it's keeping that information. It's keeping that state. That is the state it keeps so that it knows certain things that you don't have to tell it again. So that's how the normal file system works. Now, suppose you want to take your file system and you have now the client side of the file and the server side of the file. So all these files, the files that you are reading are on this side. So all the files are on this side. In the first scenario, we are assuming that there is you have a computer that has an operating system that's storing the files in the same machine where the application is running. The client part of application that's requesting for the file. So they're all on the same machine. But in the client server model, like we said, the network file system, then you have a client part of the file system and you have a server part of the file system. Now, of course, the user will interact with this one. The user will interact with this client part of the file system. So the client part of the file system will give them an interface just like the one they had in the monolithic one. But they have no idea that actually the server is somewhere else. That one they will not be told because it's transparent to them. So if this file server is stateless, it's stateful, it will behave just like this one. It will behave just like this one, where your program opens a file and reads using a file descriptor, because the assumption here is that the server is keeping the information about this file descriptor 0, which file does it go with? And this file, which was the last byte that the application actually, the application that opened this file actually read up to. So all that information will be kept as state on the server side. And so your program that is running here will just run the same way, because there is state here. And I've said state is, first of all, what does this file descriptor mean? Assume you send a message that has file descriptor and 80. The server has to process that message and find the file descriptor. It has to ask itself, but this file descriptor is just an integer. Which file exactly is it referring to? It means there is some state here that it can use to find out what this file descriptor means in terms of which file it is. And when you say 80, it has to ask itself, so this 80, where am I starting from? It means there is some information here it can refer to, and that information is in memory. So state is usually in main memory. Okay. So that's a stateful file service. And of course, you can have a stateful anything. Any program can be stateful or stateless. Well, depending on whether it's possible to do that. But now let's talk about the stateless. Now, for the stateless server, the idea here is that every operation is self-contained. The server does not keep state. So, for example, if you read the first file, if you read the file the first time, and you do another read, the server does not remember which file you read, first of all. It doesn't know which file did you even read last. In the stateful one, it knows. Just by giving it a file descriptor, it can know, oh, okay, this file was already opened and it was already read up to this point. But in the stateless, it remembers nothing at all. It doesn't keep state. So that means that every operation should ideally be self-contained. So tell me how you think the operations would look like in a stateless file service. I just want you to think about it. How do you think the operations will look like? I want to do 3 reads, each of them of 80 bytes. How would the stateless one look like? How would I write the read statements if they are stateless? Yeah, the server doesn't remember which file I read, how many bytes I read the last time. So how do you think it will look like? Okay. Someone? Adrian?
You'd have to add on to the previous bytes that you read because the server keeps resetting back to 0.
Okay, so let me try to write that statement you're talking about. So I'll say read. Would I tell it the file? Okay, let me just do the one that you said. So first I'll say I want to read 80 bytes, which will basically, actually, if I want to read 80 bytes, I'll probably say read from byte 1. So the start, I would give it the start and the finish or the end. Okay, so that means I'll probably say read from byte 1 to byte 100 to byte 80, something like that. So I give it exactly. So maybe to look something like read. Maybe I don't know how to specify the name of the file, but I would say read from byte 1 to 80. Okay. And then maybe the next one would be read. I believe this is what Adrian is saying. So the next one I'll say read from byte 81 to byte 160. Because it doesn't remember where I stopped last, it would not know. So again, if I want to read another 80 bytes, I would have to tell it exactly from where to where I'm wanting to read. And so I would read from byte 161 to byte, what was it you said, 240. And so on. Because it has no memory, it has no state. Okay, what about the file? Because we are saying also it doesn't remember which file I read. So how will I give it the file name?
You have to specify the file name each time, or you have to create a new descriptor each time before you read for the file you want to read.
Okay, so most likely I'll probably just give the file name. I'll just give the file name. Remember, it has those backslashes because it is specified including the directory where the file is. So I'll give the complete file name and I'll give the complete file name where I start reading and where I stop reading. For each file, because the system doesn't keep any state. So Most likely a stateless file server would behave that way. I'm not even sure it would have an open. Do you think it would have an open file? Because the reason for having that open the file was to get the file descriptor so that you don't always have to say, it's this file I want to deal with. In a stateless file server, I'm not sure you need the open. Do you think you need it?
No.
Maybe it can be used. You open, read, and close every time.
Yeah, I see what you're saying. I see what you're saying. Yeah, I see what you're saying. Just a minute. Okay. I see what you're saying. So you're saying if I want to read anything, I'll open file name. Okay, another way to do it, I will open file name, I'll open and I'll say the file name, and of course the mode and so on that I want to open it in. Then I maybe get a file descriptor and I read that file. I read that file. Yeah, but that's risky. You know the reason why stateless servers are there, because they actually deal with the issue of reliability. Because you see, when a stateful file server, it crashes, it loses information. In other words, if anything happens to that server, the state disappears because the state is in memory. Okay? So you see, if, for example, you had been reading a file and you are already at byte 240, and then the server crashes and it comes back up again, the state has been lost, as in which file were you even reading? All those file descriptors are kept in memory. All those, the idea of where you last read, all that information is in memory. So when a server crashes, it crashes with everything. And when it comes back up, it has no memory. It doesn't remember anything. So assume your program had been reading and now you have reached byte 240. If you issue another statement to the server which failed, it has no memory whatsoever. It has no memory. So that program will have to maybe start again. That's really just what it will have to do. But in a stateless file server, there is no such thing. The server can crash and come back again. Of course, it is not keeping state. You are not expecting it to keep state. So every operation is just, complete. So it can overcome those failures that can occur when the stateful file server is in operation. So I suspect that won't work, Craig. I suspect that won't work because between the open and the read, who knows whether the server will crash. So if you read and you send and you read with a file descriptor and the state has been wiped out by something, then obviously the server, when it comes back up, won't even know what you're talking about. So every read is actually complete, so that if the server crashes and you repeat that operation again, it will work perfectly. So I think the read will have the file name. So if you had read the file, or even you are in the process of reading the file from byte 1 to 80, and the server crashes, and you never get back the response that you wanted, the server crashes and does not remember what you did, you can retransmit that message again and it will be done perfectly. Because the server doesn't have to remember anything to do the next operation. So this would work in a stateless file server, so that each operation is independent. Whether or not there's a failure, the operation will take place. And I believe it would work the same for the write. Because if, for example, you are to write a file and you say, I want you to write the following text starting from byte such and such. So let's assume you have a write operation. You write and you write the file name. You give the file name and you give what is to be written. So let's just call it some text or some data that you want to write. So some data you want to write and where you want to start writing it from. So maybe you want to start writing it from byte 60. Okay. Obviously, maybe the data is of a certain size or number of bytes. So that operation, you can repeat it many times and it will have no effect. So if, for example, you're in the middle of a write and you're writing at a file starting from byte 60 and you're writing that data, and maybe something goes wrong and you have to repeat that operation, you can send it again and it will just overwrite what was already there. It will just write the same thing that it had written the last time. And there will be no confusion. So it works both for read and for write. And it's really a mechanism for overcoming failures, which obviously can occur in servers. They can crash, but stateful servers require that you start from the beginning because you are depending on the fact that the server is keeping some information and you don't have to say it again and again and again. But if the server crashes, that information is lost and it has no memory. That's the idea, that it crashes and it loses its memory in terms of what was it doing the last time. It does not remember. So that's the idea of the stateful and the stateless server. Of course, they have advantages and disadvantages. The stateful one obviously is faster because there's already so much information in memory. You just, get the request and you process it quickly because you already have most of the information and you give back an answer. So it works well as long as the system is reliable. The stateful, of course, takes a long time because even that read will require that you open that file, you read the 80 bytes, and then you send the result and you close the file. Whichever way it will be implemented, but it will mean opening the file, reading from it, sending the results, and saving the file. So the next read operation that comes, again, you open that file, you read from it from byte. You set the pointer to byte 81, read the 80 bytes, send back, close the file and read and send the result. So it's a lot more involving. But when there is a failure, you recover faster. You recover faster from the failure compared to the stateful. And again, I'll just refer you to where in your textbook it talks about stateless and stateful servers. I want you to look at the advantages and the disadvantages of stateless and stateful. But that's the concept behind stateful and stateless. One keeps state, one keeps no state, and state is kept in main memory. So if there's a failure, the state disappears. And now you can apply this concept to any operation, to any application which has a server and a client. Do you need to make the server stateless? Do you need to make it stateful? Again, that's a question that you have to answer for yourself based on the application that you are writing. Okay, so we're looking at the types of servers. And I was trying to explain that the different types of servers, and of course you can combine them. And so we had talked about connectionless and connection-oriented. We had talked about iterative and concurrent. And then now we mentioned the stateless and stateful. So any combination of that, for example, you look at the first, the third and the fourth there. connection-oriented plus iterative plus stateful, connectionless plus iterative plus stateless. So all those properties of a server, it depends on what you consider the right implementation of your server. You have to think about these issues to decide whether you're going to be connection-oriented. I think I talked about that. I need to talk about the iterative versus concurrent a little bit more. And I think I've basically mentioned the stateful versus stateless. One is able to overcome failure. One is not very good at overcoming failure, but it's more efficient, and so on. So you need to think about what you need in your application. I'll talk a little bit more about iterative and concurrent. And then there's the issue of how you implement the concurrent server. You can implement concurrent server using processes. You can implement the concurrent server using threads, or you can implement the concurrent server using what we call asynchronous I/O. Okay, so those ones, I will touch on them later on. I think we have one more class on Friday. Maybe I'll touch on it and conclude from there. But for now, I need to just mention, I need to go through the conceptual algorithm. Let me just look at the conceptual algorithms again. Okay, I don't know. I think I tried to look at the iterative, the conceptual algorithm for iterative server. But let me just go through it again. Connection-oriented iterative server. Okay, so this is a conceptual algorithm for the connection-oriented iterative server. Now, if you remember how the connection-oriented server works, it receives a connection request, and then it accepts the connection and creates the connection, and a connection is established. Then it receives requests from server, from client. It answers, it can receive another request, and communication will go on within that channel until the client is through, and then the connection is terminated. So if it is an iterative server, it will take one connection request from a client. So we assume that, and because you have programmed, I believe you already know this, but let me just not assume, so that if it comes in the exam, you'll say, oh, we didn't do it. So there is the client. Assume there are many clients wanting to connect to a server. If it's an iterative server, remember we said a server has a queue. If it has a queue where it receives a request for connection. So assume both of them send their request for connection to the server. It's an iterative server. So request number one will be in the queue, and request number two will be in the queue. If it's an iterative server, the server will pick the first request for connection, remember? So it will create a connection with client number one. This is client number two. So it will create a connection with client number one, okay? And remember that the accept command returns a socket descriptor. By definition, it returns a socket descriptor. So obviously the server will have executed the accept command. The server will have executed the accept command, and it will receive a descriptor, a socket descriptor. But because it's iterative, the server will go ahead and communicate. It will go ahead and communicate with the server. In fact, it actually even doesn't need to it actually doesn't even need to use the second socket descriptor. It really doesn't need to use the second socket descriptor because it's not going to service any other. It's not going to service any other client while it is still servicing client number one. So it might as well just close that socket descriptor that comes with the accept. But now it will enter another loop. After accept, it will enter another loop where it will be looping around read and write. Read a request from the server and write back a reply. Then it goes back and reads the next request from the client and writes a reply back to the client, and so on until the client stops sending any more requests or the client has finished. Okay, so notice it enters a loop here where it reads the request, process the request, formulate a response, and send a reply. And then actually, it uses the new descriptor to communicate with the client, but then it closes the connection and then returns back to accept and accepts a new connection. Then it enters the loop and uses the new socket descriptor that it goes through accept. It uses that socket descriptor to read and write, read, process, formulate, and send, read, process, formulate, and send until the client has sent all the requests that it wanted. And then it closes that connection. It closes that connection with the client and then goes back and gets the new connection. Okay, so let me go through that again. A client sends a request, the server does an accept, gets back a socket descriptor, uses that second socket descriptor that it gets to communicate with the client, and the client sends a request. The server receives that request through the second socket descriptor, responds, gets another request, responds, gets another request, responds using the second socket descriptor, and then when the client is through, it will close that connection. When the client issues a close command, then the connection that had been created will be closed. So obviously there's a connection that will be created there, and they will communicate through that connection until the client is through, and then this connection will be closed. Meanwhile, this second request for connection is still sitting in that queue. So when this connection is closed, then the server goes back and accepts the second connection request. And then the connection obviously is created based on the second socket descriptor, and they communicate using that socket descriptor, whatever else they need to communicate, and when it's finished, that connection is closed, and it's only at that time that the server goes back and accepts the next connection. So iterative because it serves one client at a time. That's basically the meaning of iterative. It iterates and serves one client at a time. So that's for connection oriented. And what is the advantage? It works best for servers with low request processing time. It means that whatever it will be doing through this connection doesn't take a long time, because if it takes a long time, the other client will wait. So the idea is that you use it when you know that the processing of clients doesn't take time. So again, that is a decision that the programmer has to make. That is a decision that the programmer has to make. And most iterative servers use connectionless protocol. Why? To avoid the overhead of connection setting and termination. Now, for connection oriented, you have to set the connection and you have to close the connection. And that adds to the time that any request waiting in the queue must endure. So it adds to the waiting time of those requests that are still sitting in the queue waiting to be served. So in other words, it's best to use it when you are using a connectionless protocol. But obviously, if your connection oriented can work with it as well, you can use it. Now, conceptual algorithm for the connectionless server, the iterative one, basically it behaves the same. It serves one request at a time. Only that this time there's no connection setup and there's no connection termination. So from what we have said is that clients simply send requests to servers. So you have a server and clients just send requests without prior communication. So the server just finds it has some requests to serve. So it accepts one request, serves that request, sends back a reply. So read the request, process the request, formulate a response, and send back a reply. And then go back and pick the next request in the queue. Now, this is an actual request to be processed. It's not a connection request. It's an actual request, like give me the balance, or credit my account with this amount. So in the case of connectionless, it iterates around the actual requests. But for each request, it goes through that process of reading the request, processing, formulating a response, and sending a reply before it goes back and collects the next request. In the connection-oriented, once it has finished that process, it goes back and accepts the next connection request. But the idea is that it serves one request at a time. So for servers with large request processing time, it will result in poor performance, obviously. If you get a request and the request takes, for example, an hour or half an hour, you can imagine that the other request will sit in the queue for half an hour waiting for this request to finish. So it will take a very long time. It's like going to the supermarket and sitting behind, standing behind those who have filled their trolleys with all kinds of things. By the time they are served, it has taken a long time and you've been standing in the queue. So iterative servers basically are not good for those requests that take a long time. Iterative servers are good for those requests that take a short time. That's the basic idea. And they're also not good for, they may take a long time because either they're doing a lot of input output or because they're using a lot of CPU time. So the long processing time could result from the use of the CPU or from the use of input output devices. Either way, iterative server is not good when the processing of a request takes a long time. Why? Because it will lead to other requests or users being delayed. Okay, I think we've talked about multi-home servers before. So that's for the iterative server, unless someone has a question. All right. Yes. Yes, Joel.
Yeah.
I
I wanted to ask, not on the concurrent, but on the question of the stateless. When you're talking about how do you keep track of the file pointer, I think, I don't know if it's correct, but I think in that case, since the server does not keep state information, why can't the client provide complete information in terms of the bounds of the file pointer, in terms of where I'm going to read?
How can the file?
Why can't the client, when they are sending the request to the stateless server, provide certain descriptions of where in the file pointer it should be read.
Yeah, but we've already described, because you were saying from byte number 1 to byte number 80. You know, this file pointer,
Yeah.
it can be positioned. I hope you know there's also another operation called rewind or something. There's a particular operation for setting resetting the file pointer.
Okay.
To the beginning. I think, if I'm not wrong, you can also set it at the end of the file. Okay. But file pointer is something that you can move. You can move it. Either it moves automatically when you read the file, or you can move it yourself. A file pointer, normally when you open a file pointer is set at the beginning, as I said. Yeah. As you read the file, the pointer moves. It is moved, I guess. I mean, the system knows how to position it. So once you read the first 80 bytes, the system will position it after the 80th byte. And once you read the next 80 bytes, it will position it. But there's also another command you can use. I think it is called rewind or something. I'm not sure, I can't remember. But if you look for one of those operations of the file, there's one for positioning the pointer. So that you can say, I want to position my pointer at a certain point, usually at the end of the file, or you want to rewind to the beginning.
Yeah.
So I think what you're asking to me, it's implicit in this statement. If I say read from byte 81, in this case, read from byte 81 to byte 60, essentially I have positioned the pointer at byte 81. The pointer must first and foremost be positioned at byte 81. Yeah. Then this read will take place. Yeah?
Yeah.
Now, so the issue here is that this read command, when you send it to a stateful server, the implementation of the read will involve several things, which are not usually done in the stateful, because most things have already been done before that. So as we say, this read will mean, first of all, you open the file. The way it will be implemented, it will include opening the file. And if it's from position 81, it will mean setting the file to position 81, and then reading from position 81 to position 160, and then closing the file. So all that will be done as part of implementing this read. So that if anything should go wrong in the process and then that transaction is not complete, if you repeat the operation, it does no harm. You just start afresh. So I think what I'm trying to say, the implementation of these stateless operations are a bit more complex than in the stateful servers. But it is implied that the pointer will be positioned. The pointer must be positioned at position 81 before you start reading.
Yeah.
Okay, so I don't know if I answered your question. Okay. Did I understand your question?
Yeah, I get it, how it's retained.
Yeah, the file pointer must always be positioned at the place where you want to start reading. So either it was positioned there before you started, or it has to be moved.
Yeah. Thank you.
Okay, so I want to talk about the concurrent server. Now, first of all, let me ask, in your concurrent server, did you use threads? Did you use processes? Did you use asynchronous I/O? Which one did you use? I'm not sure if I specified it, but which one did you choose to use?
Processes.
You chose to use processes. Did anyone use threads?
We in our group we use threads.
You use threads?
Yes.
Which group is that use threads?
I don't remember.
Okay. Why did you choose not to use processors?
For our group, you are using Windows, and Windows has a similar protocol called WinSock. Okay, and a similar
I
library
hope
to.
you did not program using the WinSock.
We did,
You
but
did?
it still uses sockets the same to the.
I know, but the operations are different, aren't they?
Most of the operations are the same. The only differences I've noticed between the WinSock and was specifically for the some minor operations where they introduce some more structures to make it easier to refer to the entire bits, like the protocol, the what's it called, when you are picking between TCP and UDP, what else, and the family for the Nini. That's the major difference I've noticed between the one used in Linux and Windows.
What
And also
about the include files?
the include files. The include files, the way it was described online, all those files were combined into the WinSock library. The TCP/IP, Uni standard, and I've forgotten the last one, but they are all included in the WinSock WinSock 2 header file for Windows.
So in your case, you just have to include WinSock header file.
Yes.
You don't have many of those include files we have in BSD sockets.
Yes, but all of the functions for sockets are still there, like creating sockets. Yeah.
I know, but look, I thought I specified we were using BSD sockets. I thought that's what I mentioned, and I expected everyone to use BSD sockets. I don't know why you took this route, Wisdom. Why did you take that route? In your group, or were you alone?
In the group.
You made that decision as a group?
Yes. Okay, perhaps we misunderstood the initial instructions to you said sockets, so
specified we were using BSD sockets. Wisdom. So you haven't used BSD sockets at all? At all? And what if I say that you go and redo it using BSD sockets? How much reprogramming do you have to do you think? It's good to read instructions carefully. Good to read instructions very carefully. I don't think I wrote it in the assignment, but I just assumed that because I even asked you to download, even in the notes it's written BSD sockets. You know that program you've written, and you cannot take it and run it on Linux, isn't it?
Yes.
You can't. Personally, I really think you should redo that program. That's what I really would prefer. But of course, if you choose not to do it that way, you will lose quite a bit of marks. To me, that's the way I will do it. So I think the choice is yours with your group. So think about it. You still have some time. You still have a lot of time to think about it. So anyway, let me, and I hope no one else has used WinSock. It's up to you because you lose almost 40% of the marks for doing that. So the choice is yours. Okay. So with a concurrent server, you are able to process multiple requests. And again here, requests could stand for an independent request, or it could stand for independent connection requests. So it's either just a request for service or a request for connection. But the idea here is that you're serving multiple of them at the same time. So the most important thing there is that it is serving multiple requests. So it's not whether the underlying implementation uses multiple concurrent processes, it's whether the implementation is serving multiple requests at the same time. Because you could use multiple independent concurrent processes and not serve multiple requests at the same time. So the question is whether or not your program is serving multiple requests at the same time. That's the most important thing. Where I said request can either be a request for service in the case of connectionless, or it can be a request for connection in the case of connection-oriented. Now, of course, the reason why we use concurrency is to improve response time. That is the main reason, because remember we said in the connectionless, it's not good to use connectionless if the requests that you are serving either are taking a CPU bound or they are input-output bound. Either way, they will take a long time. So to avoid that, to be able to serve CPU bound and input-output bound requests better, then concurrency would help you to improve the response time for the users. Because then they don't have to wait in the queue until this process that is doing a lot of input-output, completes what they're doing. And of course, the processing time typically varies amongst requests. And again, one of the reasons for using concurrency is to deal with this variable processing time. I think I mentioned the issue of supermarkets. You go to a supermarket and there are these people with huge trolleys, and maybe you're just carrying one item, and you have to, you have to stand behind them until they finish emptying the trolley. It is not fair in that sense. So in order to deal with that kind of situation, you can also use concurrency, so that each one of them feels like they are making some progress. And that's where the time sharing comes in. So the one with the huge trolley gets a bit of CPU time, then you give it to the one with just one or two items, then you iterate and come back to the one with the huge trolley, and so on. So by so doing, everybody feels that you're fair, you're giving them some CPU time. So concurrency can also deal with that situation. Okay, so as I said, one, it deals with the situation where you have significant input-output. The request, it has significant input-output, but it can also work for CPU-bound requests because they take a long time. Actually, maybe not CPU-bound, actually input-output bound, because CPU-bound, because of time sharing, they'll be preempted. The CPU will preempt them and give the CPU to another one. So mainly it's actually for input-output bound requests. And then the other reason why you may use concurrent servers is just if you have multiple processors anyway. If you have multiple processors, you can exploit them by writing concurrent servers, just so that you make good use of the hardware that you have. Now, I think we talked about blocking system calls. I think I sent you information about the blocking send. I asked you to find out about the blocking receive. I hope you have found out about that. So anyway, this is just an explanation for each of these reasons why you need to use concurrency. It's just more detail about that. For input-output bound requests, it means that you will overlap processing with input-output, so that if a program reaches a point where they want to do input-output, you suspend them and you run the one that is ready to run. Because obviously input-output means the program will be suspended while whatever is required from the input or output device is being requested, is being brought into memory or being sent to the device for output. So in order not to waste CPU time, usually such processes will be suspended for a while and then another process can be run. Yeah. So, or else if that is not done, if you do it the iterative way, it means that the CPU will be idle. If you use an iterative server and you have an input-output bound program, then obviously the CPU will be idle quite a bit of the time. Whenever the program is doing input-output, the CPU is idle because there is no other program to run. So to utilize CPU time in the best way, you can have multiple programs and run them concurrently. And I've already mentioned about the fact that the variable processing time can also be a good reason to use concurrent processes, and so that each and every process is making some progress. And then the issue of having multiple processors, you can exploit the multiple processors for concurrent processing. So now, to look at the conceptual algorithm, there's a concept of the master process and the slave process. Now, the master process is the one, and I think I'll finish with this. Okay. The master process is the one I was talking about in the other set of slides, where you have several client programs and you have a server. You have a server that has a queue for requests. And then when it receives a request from one client, it creates a slave process to deal with that client. So it creates a slave process to deal with that client. Then when it receives a second request, it creates a slave process to deal with the second client, and so on. And so you end up having several concurrent processes running. Now, this is the master process, and these are slave processes. And remember that the slave processes are created from the master. So it's the master that keeps creating the slave processes to take care of the client requests, so that you can have multiple clients being served at the same time. So it is possible to achieve a concurrent server using a single process. That is the asynchronous I/O method. With the asynchronous I/O method, you actually don't have slave processes. You just have a single process. But with the multiple processes and threads, then you have multiple processes or multiple threads. But with the synchronous I/O, you just have one program. And that program is alternating between all the different clients at the same time. So it would look something like this. So you have multiple clients, and they are all contacting a single server. And the server is alternating between them. It's alternating between all the different clients that are trying to contact it, or that have contacted it. So whenever this one sends a request, it begins communicating with it, and at some point it will stop and change and deal with another one. It will stop at some point. When that one is not ready, it will continue with that one. Remember that a process alternates between CPU bound and IO bound. So whenever a process changes and it needs to do input output, it suspends it, or it's suspended and it moves to the next one and the next one and the next one. So with this single master, not even master, it's just the single server, it alternates between all these processes using just one process. That is a synchronous IO method. But with the processes and the threads, you always create a slave. The master creates a slave to deal with the clients, and then the master continues to listen for requests. So that's the idea of the master and the slave. So in concurrent processing, you have the master and the slave. And so you have to know the conceptual algorithm for the master and the conceptual algorithm for the server. So let me just go through this, and I think I'll stop with this. So here we assume a concurrent server. The concurrent server begins execution and creates a socket. And of course, once it creates a socket, it does all those things, bind and so on. They're not included here. It creates a socket, it binds it, it listens, and then now it waits for the next request. So waiting for the next request is at the point where you talk about accept. So this statement here is actually loaded. There are many things that are taking place here at this point. I've said you create a socket, you bind an address to it, and then you listen. And then at this point, you wait for a request by issuing an accept command. Now we say that an accept command only returns if there is a request, and it returns with a new socket descriptor. So with that new socket descriptor, you can then create a new process to use that socket descriptor to communicate with the client. Okay, so it creates a slave server process, either a process or a thread. It creates a process to handle the request it has just received from here. So it has received a request after waiting. When it gets back a response that there's a request, it creates a process. And then the slave process now handles communication with the client. And this slave process, of course, after forming a response and sending, after forming a response and sending the reply to the client, the slave process exits. Yeah. Now, meanwhile, this one, once it created the process, it handed over the process to the client, or handed over the client to the process, and then this one, the master loops back. So basically, the master process is you begin execution, you open a socket, you bind an address to it, and then you listen and create the buffer for requests, and then you accept any new request. If a new request is there, you create a process, or you fork a process if you're using processes, or you create a thread, and you hand over that new socket to that new thread or process you have created. So while that new process or server is dealing with the client, the server loops back. It loops back and checks if there's a new connection request. So there should obviously be a master process, which is this one. I think I've described it. Create socket, bind, and then call the receive. No, this is connectionless. This is connectionless. So for connectionless, you call the receive after bind, and then you create a new slave process and you repeat, and you go back and pick the next request, and then you repeat. But this is important. First of all, I have noticed that there are students who put this call before repeat. This call is within the repeat. Remember, it's within the loop. It's not outside of the loop. It is inside the loop, because this server will be looping, getting a new request, creating a slave, then going back and picking a new request and creating a slave. go back and repeat get a new request and create a slave. So this receive is within the loop. It is not outside of the loop. But so this is the master for connectionless. And the slave for the connectionless, once you create this slave, in other words, once you create this slave, that slave, and you hand over the new socket to it, then you receive the specific request from the client, because now you're dealing with the client directly. You receive the request, you process the request, you formulate a reply according to the application protocol, and you send it back. And you exit. But this can also be a loop. This slave can also loop. This slave can also loop, because if there are multiple requests within a connection, then obviously it will go back and receive a new request. No. This is connectionless. No, this is connectionless. Since there's no connection, there's no need to loop. It is connectionless. Sorry about that. It is connectionless, so there is no loop. If it was connection oriented, then it would have a loop. It is connectionless, so there is no loop there. Okay, I think I'll stop there. And I hope that that conceptual algorithm is okay. And remember, I have said that in the exam, you will be asked only specific parts of this algorithm to implement. Depending on the question, you can be asked to implement any part of this algorithm. Now, if you are to implement any part of the algorithm, please make sure that you implement only what is necessary. Only what is necessary to answer that question. And I think in the morning I was trying to say, I hope you understand what it means to receive a request, those things that are put in red, that you understand what they mean. You receive a request, you process the request, you formulate a reply, and you send a reply back. I hope you know what they mean so that you can interpret them in any context, any application that you are given, you will understand what that means. So if you are told, for example, write a program to process the request and the application is described, whatever the application is, you will understand what process request for that application means. Now, because of time, I think I will leave the concurrent conceptual algorithm. But I would want you to become familiar with these conceptual algorithms and program according to the conceptual algorithms. Where you have not done it, you only have yourself to blame, because I think I already said that you program according to the conceptual algorithm. Was there any misunderstanding on the issue of conceptual algorithm? Did anyone have a misunderstanding or something that was not clear about what the conceptual algorithm was talking about? No? You're okay? You're okay? All right, I'll take it that way. So I think we'll stop there. Okay. So what are we left to cover? I'm left to describe the asynchronous I/O I want to believe that the thread, you know how to program with a thread, but maybe what you need are what are the advantages and disadvantages of programming with a thread vis-a-vis the advantages and disadvantages of programming with the process. In other words, comparison of those methods of programming. Concurrent server. What are the when should you use one and not the other? What advantages do you have in using process vis-a-vis thread vis-a-vis asynchronous I/O? I think that's one of the things I will cover. And then I will cover the stub, which we started today. That issue of the stub and distributed programming, I will cover that as our last topic. In other words, converting from socket programming to distributed programming is actually not that complicated. Once you understand socket programming, you can easily understand distributed programming. The other way around is a little bit more difficult. In fact, distributed programming arose as a result of programming with sockets and finding programming with sockets to be a little bit more difficult for some people. So distributed programming was to make it easy. So if you understand socket programming, distributed programming is very easy to understand. So I'll conclude with mention of distributed programming and the issue of stubs, which I heard one of you mention today, because I believe you already know what that is, but it's important for us to cover it. So those are the two topics I think I'm left to cover, unless there's something else you think I haven't covered. Yes. Hassan.
Yes, madam, I have one concern.
Yes.
As a group, we use the WinSock.
Oh, again. No. You just go back and program.
Pardon?
If you use WinSock, I've already said you just go and program again. Are you in the same group as Wisdom?
No. I'm in another group.
No. How many groups? If any group used WinSock, I actually don't know how you did that. First of all, let me just, how many use BSD sockets? I could be assuming and then the whole class programmed its WinSock. How many people use BSD sockets? How many groups? Okay, I've seen. Yeah, that's what I expected. Anybody who didn't use, just go and change your program. When you are through with it, let me know, and I will open the classroom for you to submit. But you only have up to the end of this week. Hassan, I think I'm responding to you. Have I answered your question? Hassan?
So you are saying we should start from scratch and use.
Okay,
BSD.
let's put it this way. Remember, initially my idea was that you program all those 6 programs, and at some point I found out that you are behind, or there was some complication with the clock. Was it not the clock, the calculator? There was some calculation with this problem with the calculator. So I said that you only submit the one with the shop, online shop, bookshop, online bookshop. So this is what I think I should do. I feel that maybe the ones I will mark will be the online shop. Those are the ones I think I should mark. So if you do the online shop and you submit it, that will be fine for marking purposes. The cart remains as it was done. I have already asked you to revise it, but somehow it will be combined with what you did in the cart. So even if you get 100% in the revision, it will be combined with what you did on the day we were doing the cart. It will have a higher percentage. I haven't quite worked it out, but the reason I was just trying to avoid a situation where somebody gets a 0, because some of you, I looked at the papers and I was even wondering where the marks are going to come from. So, am I communicating? Is that
Yes.
okay? Is that okay?
Yes.
Yes.
Yeah. But that doesn't mean that you don't think about that question, that the questions that I gave. I think it's just because somehow we got delayed and there was a lot of holidays in between that I think we lost time. But for me, as long as you know how to use sockets, I think we have achieved the goal. If you can write a connectionless client and server and they communicate, I'm happy with that. If you can write a connection-oriented server and it communicates with a client, I'm happy with that. As long as you know how to use those socket primitives, I'm happy with that. So it's not the number of programs. The number of programs was to help you practice and to see different variations of programs and to see whether you can program different programs with the same concept. But for marking purposes, I will stick to the other one. I'll stick to the online bookshop. So Hassan, I hope I've answered your question.
Yes. Thanks.
Yeah?
Yes, madam. It's clear. Thanks.
Yeah, so that should make your reprogramming easier together with Wisdom and group. Okay, thank you very much. Our last class will be on Friday, and I think the exam, if I'm not wrong, it's on Wednesday, is it?
Yes.
Yeah. You look at the past papers to get an idea of what kind of an exam you expect. So please don't come to the exam and say you had no idea. Just look at the past papers and you get some idea. Thank you very much. Have a good evening.
And you too.